Today we are starting a new unit on matrices. So the main topic for today are going to be matrix operations. Now, when we say matrix operation, a matrix is a arrangement of numbers and rows or numbers in rows and columns. It's not the movie The Matrix like you might have thought originally. You can kind of think of an Excel spreadsheet is kind of like a matrix, just written out a little bit differently. So you will have something that looks like this with a certain number of numbers in there written in rows and columns. So let's go ahead and take a look at this. So we have our first example here. So this is a row. Everything across is the row versus everything down, this is your column. Now, one thing you can kind of think about to help you remember is like the columns of the White House. The columns go up and down. So if you ever get kind of mixed up on which one's rows and which one's columns, think about the columns like out in front of a house there. It's the up and down part. So when you're writing your dimensions of the matrix, it's telling you how many rows and how many columns. And it always goes rows first and then columns. So something that is a 3 by 4, what that means, it has 1, 2, 3 different rows and 1, 2, 3, 4 different columns and an equal number in each row and in each column. So there are 12 different data entries then in that matrix. So if you have a matrix, you can then identify specific entries in that matrix by looking at specific rows and columns. So right here, this R2 is saying row 2, column 4. So you're going to go row 1, row 2, and then column 1, 2, 3, and 4. So row 2, column 4 would be this one right here, which in our example here, row 2, column 4 would be data entry 2. So the next one is saying row 4, column 1. So we have row 1, row 2, row 3. Row 4 does not exist for this one. So we can use DNE for does not exist. Now, there are a bunch of different matrices. You can have pretty much any number of rows and columns, and there are some special ones. A row matrix is one that only contains one row. So it can have a number of different columns, but there's only one row. So however many data columns you want, that's fine. And in each of these different entry points here, you could have numbers like 1/4, you could have a number like pi, you could have the square root of 2, or you could just have kind of a normal integer. Your column matrix is going to be very similar. It's just made up of only one column with any number of given rows to go along with it. A square matrix has the same number of rows by columns. So your dimensions here would be something like A by A, because you have the same number of rows and columns. So a 1 by 1 works, or a 2 by 2, and so forth and so on. Another special matrix would be the zero matrix. It can be any matrix as long as every single entry in it is 0. So any given number of rows or columns, but all of those are 0. So that's a little bit about the different types of matrices and everything and how to read them and the dimensions. Now we're going to start actually doing some different things with them. So if two matrices are equivalent, that means that every single entry corresponds with the other, whatever it's equal to. They have to be equivalent if your row 1, column 1 matches up with the row 1, column 1 in your other matrix. So for these ones, you can't have different dimensions because then you won't have enough to line up here. Okay, so they have to be the same dimensions. And basically you just line them up and say, well, 1/2 of x has to equal 5. So then x has to be 10. So then you just look at each corresponding spot and you set those equations up, setting them equal to each other in order to solve for these. So 15 has to equal y plus 2, therefore y is 13. W plus 3 equals 15, so therefore W equals 12. And 25Z equals 125, so therefore Z has to be 5. So those are equivalent matrices. Now looking at these ones, what we can do is we can go ahead and combine different matrices through addition and subtraction. So this only works if everything, once again, has the same dimensions. So you cannot add something that is a 2 rows by 1 column and 1 row, 2 columns. We cannot add these. So if you are told to add these together, you would say that does not exist because I cannot line up the corresponding spots in terms of row 1, column 1, row 2, column 1, and things like that. So it just doesn't work. If, though, they do have the same dimensions, so for instance, this first one is 3 rows by 1 column, and we are adding something else that has 3 rows and 1 column, that means I can match up my corresponding spots and then combine them. This one is through addition, and so our answer here, our row 1, column 1 would be 2. Our row 2, column 1 would be -3. And our third row, first column, would be -5 overall. This would be my resulting matrix. For the negative, when you are subtracting them, depending on it, I would strongly recommend changing this to addition and just changing every single item in the second matrix in order to make sure that I do subtract each and every one. So now I can do 5 and -3/5. And so if you need to do some scratch work and everything, find common denominators, that would give us 22/5 as my first row 1, column 1 entry. We have 1/2 plus 6, which is equivalent to 13/2. So these two, my resulting matrix again has the same dimensions as the other two when I combine them through subtraction. So we can add and subtract matrices. We also can scale matrices. So scaling it is kind of like changing the stretch of a graph, if you would think of it that way. We're going to do the same thing here with the matrices. We're just going to have to multiply each and every item by whatever the scalar is out in front. So the scalar here is -2, which means I'm going to multiply every row and column and every item in those rows and columns by -2. So I would get -10 and +10 for my first column. For my second column, I would get -6 and -4. For B, I would like to scale my matrix first. So I'm going to scale that second matrix by a factor of 3 and then combine them through addition. So go ahead and multiply each term by 3, and now you can combine all of the items that are in the corresponding spot. So our final answer would be 20 and -12 for your first row, -18 and -5 for your second row, and 43 and -13 for your third row. So we can use adding and subtracting and scalar multiplication to solve different matrix equations in different ways. So there's so many ways of solving this. What I'm going to do is I'm going to try to get matrix M by itself. So I'm going to go ahead and add this matrix to the other side. So I'm going to show it here. So I'm not changing any of the values inside the matrix because I'm adding it to the other side. So that's going to cancel that out. And so -4m would have to be 28, -4, 32 for my first row, -12, 4, and -32 for my second column. I said row, sorry. First column and then second column. Then you have a couple of options. You can just kind of work backwards if you would like to figure out what m is. So -4 times what gives us +28, or you can do a scalar multiplication of -1/4 in order to undo that -4 in front of m. So the first item would be -7. The next item in that column would be 1, and then -1/4 of 32 is -8. And then the other one would be a positive 3, a negative 1, and a positive 8 when we divide those. Okay, so this would be our final answer for M. So that's the gist of matrix operations with adding, subtracting, and then scaling. We're not going to talk about multiplying matrices because that's going to be a little bit more lengthy of a process, so that will be forthcoming tomorrow. Okay, thanks for listening. I hope this helps, and let me know if you have any questions.